Okay, guys, now in this question, we're confronted with a scenario that's appeared a couple of times on the Leave Cert in the past about the speed of a satellite as it orbits about a planet of mass m and radius r at a height h. So if we read the story, a satellite of mass m, small m, orbits at a height h above a planet of mass capital M and radius r. Find the speed of the satellite v at any instant in terms of m, h, and r. Now, this is a standard practice question. Okay, so first of all, let's put our information in onto the diagram. Clearly, this is our planet here, and the mass of this planet is capital M. So let's put a capital M in there. There's the center of the planet. Now, the radius of the planet is r, so we know that that distance there is r. And then the satellite is orbiting at a height h above the planet, so that height there is h. And then we know that the mass of this satellite here is small m. Okay? Now, we know from Newton's law of gravitation that all objects exert a force on each other, which is proportional to the product of their masses and inversely proportional to the square of the distance between them. So we know the formula for the gravitational force is g m1 m2 divided by d squared. And an important thing to note here is that d is always measured to the center of the planet. So from the satellite to the middle of the planet. And I hope you can see here that in our situation, d is going to be equal to r plus h, the radius of the planet plus the height of the orbit. Now, we also know that all objects moving in a circular path experience a centripetal force. And we've been told that this particular satellite is whizzing around the planet. Notice that the velocity in any given time is a tangent to the circle. Important note from the circle chapter, from the circular motion chapter. So we're moving around there with a speed v at any given time. Now, according to Newton's law of gravitation, the gravitational force trying to pull that mass in towards the planet is big G by little m by big M, g by the product of the masses, so simply gm1 m2 over d squared. M1 is the mass of the satellite, little m, m2 is the mass of the planet, big M, and then divided by the distance between them squared, which is r plus h to be squared. Okay, so the gravitational force trying to pull the satellite in towards the planet is g little m big M over r plus h to be squared. Now, we know that all objects moving in a circular path experience a force towards the center of the circle called a centripetal force. Now, the only force acting towards the center of the circle, the center of the planet in this case, is that gravitational force. So the centripetal force is the gravitational force. So we call it the centripetal force Fc. And that's equal to g by little m by big M over r plus h to be squared. Now, in terms of centripetal force, we have two possible formulae that we could use. We can use m omega squared multiplied by the radius of the circle, in other words, d, the distance to the center of the planet, or we can use mv squared over d, where in both of those cases, m is little m. M is always the mass of the object that's moving, and it's clearly the satellite that's orbiting the Earth, not the other way around. Now, we've been asked to calculate the speed, and obviously the one that calculates speed is this one here. The other one we would use if we were looking for omega, the angular velocity. So I've chosen the one that's going to allow me to find the velocity of the satellite at any given time. So all we got to do now is very, very simply put this in here instead of the centripetal force, because remember, that is the centripetal force. For a stable orbit, the centripetal force is equal to the gravitational force. So that's for a stable orbit. Okay? Now, this means that mv squared, little mv squared, divided by the distance to the center of the planet, which is r plus h, equals g by little m by big M divided by r plus h to be squared. Okay, so the centripetal force is equal to the gravitational force. Now, we'll notice here that we have a small m on the left and we have a small m on the right. And what that actually means mathematically is that the mass of the satellite is absolutely irrelevant. The only mass that's important here is the mass of the planet. So the cancelling of the little m's, that's what that means. Now, also we notice that we have an r plus h on the bottom on the left, and we have an r plus h to be squared on the bottom on the right. Now, that means that the r plus h on the left is going to cancel with one of the r plus h's on the right. So we'll do that all on the next line. So we're left with v squared, because m is gone and we've cancelled the r plus h on the bottom, equals big G by big M. Big G is the universal constant of gravitation, multiplied by big M, the mass of the planet, and divided by r plus h, because remember the r plus h on the left cancels with one of the r plus h's on the right. So that's what v squared is. Now we've been asked to calculate the velocity, so that's going to be the square root of that mess, square root of gm over r plus h. And that will be meters per second. Now that is an extremely important derivation. It just requires a knowledge of Newton's law of gravitation, that F equals gmm over r squared, over r plus h to be squared, and also knowing that the centripetal force is mv squared divided by the radius of the circle. And in this case, the radius of the circle is r plus h. So v equals root gm over r plus h. Now, what we do next is we use the answer that we obtained in part 1 to find out the speed of this particular satellite that's in orbit at 1,000 kilometers above the Earth's surface. Now, the important constants we're given, we're told that the constant of gravitation is that. We're told that the radius of the Earth is 6.4 by 10 to the power of 6. And we're told that the mass of the Earth is 6 by 10 to the power of 24. So literally, guys, all we got to do now is plug these numbers into the formula that we derived just a couple of seconds ago. So here goes. In part 1, we came to the conclusion that V is the square root of gm divided by r plus h. Okay? Now that means that V equals the square root of gm. Now g, according to the information we're given in the question, is 6.67 by 10 to the power of minus 11. We're given that just over here. The mass of the Earth, given here, 6 by 10 to the power of 24. Divided by the radius of the Earth plus the height of the orbit. Now the radius of the Earth is 6.4 by 10 to the power of 6, plus the height of the orbit. Well, it's 1,000 kilometers up into space. Now, guys, I've deliberately made an omission here. It's just I haven't done it yet. I've put in kilometers here in the bottom right-hand side, and that is an extremely common mistake. Okay, we were told it's 1,000 kilometers, but the standard unit of distance is not the kilometer, it's the meter. So we need to convert that to meters by multiplying by 1,000. So just make absolutely sure that you remember to do that. Okay? Now, from here on, it's a matter of are we able to use our calculator? So we have 6.67, and then if you have a sharp calculator like me, EXP, if you don't, multiply by 10 to the power of, on a Casio calculator, the power of minus 11, and then we have to multiply that by 6 by 10 to the power of 24, and then we have to divide by, in brackets, 6.4 by 10 to the power of 6, plus it's at a height of 1,000 kilometers, so that's 1 million meters. So just make sure you count your zeros properly. So that's 1 with 6 zeros after it. Close your brackets, and that's equal to that. And then we need the square root of our answer. So our answer is the speed of the satellite is 7,353.98 meters per second to 2 decimal places. Now, obviously, that is an absolutely shocking speed. It's almost 7.5 kilometers in a second. So the road from Dublin to Limerick, which is approximately about 170 or 180 kilometers, that would happen in less than 30 seconds. Okay, it would happen in about 18 seconds or thereabouts. So these are unbelievable speeds. The satellite has to move that quickly to avoid the Earth's gravitational pull and to actually stay up there. If it slowed down, it would just literally fall into the Pacific or the Atlantic or on top of our houses. So it's very important that they're moving at this speed. It keeps them up there. If it slowed down, it would collapse into the Earth. And if for some strange reason it got a jolt and it sped up, it would just spiral out into space. So for a stable orbit, speed of that satellite is 7353.98 meters per second. Now, did everybody understand that question? Okay, that's brilliant. Okay, no questions? All right, we'll move on and do another one.